with additional penalty function, variable function. In some cases, we might have non-differential function. For instance, if you consider a perfect variable function, the variable function looks like this. When we have this interval convex constraint set, so only feasible point is inside this interval. For this convex constraint set, the perfect additional barrier cost function will be this. So 0 for inside feasible point, and infinity outside for whole outside point x. So it is because when your point x is outside of convex constraint, then the additional barrier function will have infinite value. So your objective function plus your barrier function, cost function cx, will have infinite value no matter what function value you have. And so we can guarantee that the minimum point argmax of fx plus cx inside the convex constraint. Also, since the cx function having flat minima for entire inside convex constraint feasible point, we can also say that this cx additional barrier function does not perturb your solution of fx. So the additional barrier function does not change your optimization solution. You will have the same x star with original problem with convex constraint set. Okay, so this additional cost function is a very nice, perfect function. But the problem is this is non-differentiable. At this point, we don't have a gradient. And this is not smooth function, so and not a strongly convex function. So it is very, very difficult to guarantee some convergence speed with gradient descent algorithm. Proximal gradient descent method is invented for this case. So this approach is especially good for such non-differentiable additional variable function. So for differentiable objective function g, we can easily define gradient descent step like this. xt plus 1 is equal to xt minus step size gamma times gradient g xt. And this is equivalent with this interesting representation. So this is argmin gxt plus gradient of gxt transpose y minus xt. Actually, this is the equation for the tangential line function, tangent affine function at point xt. And plus, this is the distance to xt. So basically, xt plus 1 is the solution, argmin, of your tangential line at xt, your current point, plus 1 over 2 times step size times the distance to xt. Since this is an affine function, you can decrease this tangential line affine function as much as you want. As you move away from xt to the opposite direction of your gradient vector, you can decrease the function value. But because of this constraint, you cannot move away infinity. You have some restricted range of update. Okay, and that is essentially equal to xt minus step size times the gradient at point xt. consider the objective function f that is summation of original objective function gx and some additional cost function hx. And we consider g, we assume g is a nice function and differentiable. And h is a simple additional cost function, but it could be non-differentiable. Okay? In that case, we can define proximal gradient as follows. xt plus 1 is equal to argmin y gxt plus gradient of g at xt transpose y minus xt. This is the tangential line of function g. And since g is differential function, so we can define gradient of g xt transpose at every point xt. And again, we have a restriction on your movement, your distance, by the Euclidean distance term, 1/2 step size times y minus xt norm square. Plus, we add the additional cost function hy, which might be not differentiable. Okay? So this part comes from the simple gradient descent algorithm or concept just for the first function gx, because hx can be not differentiable. And since we are trying to minimize summation of g and h, we have to consider h as well. So here we just add hx function. And this is equivalent with this representation, because this because this is just constant. So because this is just constant, and we are trying to find the argument, we don't care about the function value, we just care about the argument, the point, the x that minimize the function. Okay, so you can add and subtract any constraint very freely. That does not change your solution, because you are trying to find argument, not minimum value. So you can add, you can remove this, and you can add y, okay, gradient of g xt normed square times gamma over 2. Then basically this equation is equal to 1/2 gamma times y minus xt minus gamma times gradient of g xt normed square. So you can easily check that this and this is exactly the same. And since this and this just constant with respect to y, so even if you change y, this and this term never change. So you have this equivalent form. And this operation is called proximal operator. Okay, so proximal gradient descent approach, basically just learn the simple gradient descent with function gx, and then apply proximal operator with function h. Okay, and the proximal operator defined like this. So this is the definition of proximal gradient descent. Here we never use gradient of h. We just use the gradient of g. Okay. Of course, to solve this might be not easy task, but at least for the definition for proximal gradient descent, we don't say any gradient of h. Okay. Right. So this is generalized gradient method. It's kind of. So every time we update input x with proximal gradient descent concept, and the update ranks and update direction, we can consider this as ungeneralized gradient. So every time we update xt plus 1 is equal to xt minus step size times generalized gradient. Okay, so this is proximal gradient descent method. So why this is very useful? Let's consider an interesting example. So when h is equal to 0, then this is the original gradient descent algorithm, because we don't care about any function h, so we can simply remove this part. Then we have exactly the same gradient descent approach. And the projected gradient descent approach is the case when h is this indicator function of your convex constraint set, which is equal to 0 when your input x belong to the convex constraint. If the input x is outside of your convex constraint, it has value infinity. Then this update is exactly the same with projected gradient descent approach. So consider this point. Here we are trying to minimize the distance to your gradient descent, original gradient descent point from your point of convex constraint set, because this hy is equal to 0, so we can ignore this part when y belongs to convex constraint set. But this value go to infinity, so we don't care about the outside of convex constraint set from this equation. So this is equivalent to the projected gradient descent approach. So we can define the simple original gradient descent, and we can define projected gradient descent algorithm using this generalized gradient descent. This is the proximal gradient descent concept. So with this proximal gradient descent concept, what is good thing is we can guarantee convergence speed. Okay, so as I told you before, the additional function h can be non-differentiable, and h function can, so if the h function is non-differentiable, then it is non-smooth. Okay, your gradient is not continuously change, so this is not smooth function, non-differentiable function. So if your function is non-differentiable, we cannot bring the convergence speed of for the case of smooth function, beta smoothness. When we have beta smooth objective function, we can guarantee roughly 1 over t convergence speed with a learning rate gamma equal to 1 over beta. But we cannot do that for this case because h function is not differentiable. But with proximal gradient descent algorithm, we can do this one, because we just care about the differentiability of function f, and we just care about the smoothness of function f. Function g. So here, we just need to care about the smoothness of function g. Because everything of h already, we encounter everything on h